Thank you. Okay, thank you very much. Thanks Ian for the great introduction. So my name is Christos Tachtatzis. I'm from the University of Strathclyde. I should say that I'm not an epidemiologist. I'm an electronic and electrical engineer by background, so I'm a technologist. So please take it easy with me. You know, all matters epidemiology. I think next. Yep, there you go. So I think Ian covered most of that, but a couple of other things that I should say is that my research is on computer vision, image processing, hyperspectral imaging in particular. I've done a lot of work in kinematics. I've been working in the place of livestock farming for about 20 years now. So I started working with kinematics, and then also micro Doppler radar, which I'm not going to cover today, but that's another passion of mine. So I'm also the lead of the Strathclyde lead for the Sustain AI Center for Doctoral Training, which is the collaboration of 4 universities, the University of Lincoln, Aberdeen, Queen's University, Belfast, and Strathclyde. And this aims actually to train PhD students. We aim to train 60 PhD students over 5 cohorts. And we're thinking that this is necessary to have a crossbreed between AI scientists and animal science and bioscience expertise. Because I think the two are kind of different, but they can work collaboratively with each other and they can merit from each other. The other bit which I'm working on is the digital data chain. So this is a project, Strengthen Places project, which is, looks at the digital data chain in south of Scotland and North Cumbria. The work I'm going to present today is from that project, basically. So you can see some of the work we'll be doing within the digital data chain. And finally, I've been participating in SAFARI, the Special Advisory Group for AI to the Scottish Government. So this is kind of my background, so you know where I'm coming from. And then I'm just going to go on and show you a case study that we have from the digital data chain. So, but when I present this work, I think I'm going to be thinking this animal in the middle has been a system, and you probably know more than me. You have different inputs to the system. You know, you feed your animals, you water them, the labor, genetics, environment, fertilizer, everything that you put into the system. And then you have certain outputs, you know, maybe the milk and meat potentially that you want as a good product, but maybe you want to minimize greenhouse gas emissions. You want to manage your manure or even manage the ecosystem, you know, by diversity of your grasslands. And on top of that, what we have at the top is we have the health and welfare of the animal. And then we have also social and cultural aspects of positive welfare. So the consumers now want to know that the animals are having a good life, and what this means is different for different people. But I think we have a potential to give even more about to the consumer about what is the life of the animal that they're getting the product from. So I would like you to think of that as a problem of product optimization. And if we look at the average herd sizes in the UK are increasing, while the number of producers actually are decreasing. So you can see the two trends. So the blue one is you know, decreasing number of producers. So we're just going down while the herd sizes are increasing, which means we have farms actually, we have more animals, and that in itself creates a challenge. At the same time, if we look at the milk production is increasing. So what's going on here? We have less farms, we have more animals, and increased milk production. And I think this is only possible through the use of technology. So and if I look at the technology that I was involved to initially, when I finished my doctorate about 2007, I was finishing my doctorate. I finished in 2009 my doctorate, but I was working as a postdoc on this project. There was a development of a collar system, what you will call maybe Fitbit for cows, which was trying to use it to detect ostrus, so you can do the artificial insemination, a different type of AI, right? In this sense. So the idea actually was, can we detect the activity of the animal as a proxy to ostrus? And the device was quite simple. It was a 3-axis accelerometer, which was mounted to the neck of the animal. And you had these signal traces, which look quite noisy. But by processing that, then we were able to detect that. And I guess at the time, we didn't call it the Internet of Things. Maybe today you will call it the Internet of Things. We had a small microcontroller basically there. We had to have different demands. We had to have a long battery life of 7 years. We had to have our algorithms to do the detections. But it couldn't be operated in a small 8-bit microcontroller with a hardware demand. So there was a lot of challenges in doing that. And then the other bit that it had a wireless radio, so it can communicate to the farmer that this animal needs your attention. So that's how we started around that time. So like I said, this is the kind of the device, a small sort of a logical block diagram of what the device consists of. Like I said, you have the ultra-low power microcontroller, 3-axis accelerometer, some flash memory and battery, which, by the way, battery was the most expensive component of the whole lot, plus a radio. And the idea, we couldn't take all this accelerometer data and transmit it over to a base station for processing to the cloud, right? So we had to do the processing on the actual device. And then we had to trade on that between accuracy and precision of what we were detecting versus the energy cost to transmit this information. So that's where we start on the heat detection. But then we realized we can do additional stuff. And that was, we can detect when the animal is eating, when the animal is ruminating, or doing something else, some low activity state. The rumination is a rhythmic motion, which, as the animal chews, takes a bolus up, chews it, then swallows it, take another bolus up, chews it, swallows it. So it has a rhythmic pattern, which you can kind of see in here. You can see the different peaks. And that gives an indication of the rumination, while the eating was like a high activity motion. I'll show you in a bit how this goes, but I would like to highlight here, that the data rates that we have here, they're high to maintain battery lifetime, but they're quite low for today's standards, right? We're talking about 450 bits per second, which is not that high, really. So if we take this data, basically from that trace on the top right-hand side corner, and we do some feature extraction, and we engineer a lot of features, and that was the idea of us sitting there and trying to break our heads to see, what is good features actually to represent these 3 activity classes. Then we end up with these 3 clusters that you see. The other is the red class, rumination and eating. And what the 2 features that you can see there is the energy expenditure, so it's a metric of energy of the accelerometer trace, and the other one is the frequency content. So you can see the rumination, the green cluster over there, it has medium energy, but very high frequency content. It's quite repetitive in terms of motion, while the eating is sort of high expenditure, but no frequency content, low frequency content, rather. So the color that we have there, it's processing that on the device, and every 90 seconds, it communicates an activity state, which it thinks the most probable activity that happened for the last 90 seconds. So if you present now how it's been presented to the user, that's what the processing of the device is. The device communicates these clusters. And then if you plot them over a period of time for individual animals, you get these traces. So the top one, actually, what you have is sort of like the activity. And then you have the green is the eating time that the animal is using. And the rumination is the blue. And then you can see, for example, when the animals get inseminated. And then you can have different deviations. What you see, that gray band is what we consider normal. So for every animal is different. So you're building a database of what's normal for that animal. And if you start deviating from that band, then you're saying something is wrong with my animal, basically. So in this particular case, for example, if we look at the bottom one, we see that something is wrong. The green and blue traces, are dropping, but we don't know exactly what's wrong with that animal, which says there is something wrong with an animal. It's sort of like an outlier detector. So the next stage is, how we can use it in a diagnostic way, so we can tell and confirm that this is mastitis to the farmer. And the only way you can do that is basically through merging it with additional data sources. So a lot of the farms, actually, they will have these machines, the milking robots, the animals go and getting milked by themselves at their own will. They're going into the robot as many times as they want. But the robot is an opportunity actually to do another measurement. In this case, it can measure conductivity per quarter. It can monitor fat content and lactose and so on and so forth. So by bringing this data from the robot, basically, and combining them along with the data from the collar, then we can create this map. So what you see at the top is sort of like an alert detector, basically, which is binary on or off. There is an alert for eating, an alert for conductivity, and so on. But combining all these information together, then we can confirm what's going on with this animal. And in this case, actually, we can predict, for example, its mastitis. So what you see at the bottom there is sort of the conductivity per quarter, lower left and so on. So fusing data together is the only way that you can increase your diagnostic capability. And then, along with this technology actually that we developed, so that company was a spin-out from the University of Strathclyde. It got sold to an Israeli multinational called Afimilk, and we don't have a stake on that anymore, but we just keep working in that same area. And I worked with a number of these different sensors that have been deployed to the animal, right? So I've worked with boluses, pedometers, collars, milking robots, tail sensors, and so on and so forth. And they can do different things, right? They can give you the fertility optimization, like the collar, diet optimization, for example, eating and rumination, and if you have different mix types, animal health, milk production, and so on. But the problem is that you have too many devices, and these devices are invasive. So the work that I'm currently doing is trying to convert, basically, something like this to an animal, what would I call the happy cow, basically. So you cannot deploy all these devices together at the same time, right? And they give you overlapping information. So we need to kind of simplify. So as part of the digital dairy chain, basically, we're trying to push towards a new sensing modality, what we call remote and ambient sensing, that eliminates all the wearable sensors. And in the first instance, we're trying to apply this into a shaded environment, a house environment. And we have different technologies that you can apply there, where the sensors are not on the animal anymore. They're instrumenting the shed, and then they're monitoring the animals within that shed. And we have different sensors to use from. Cameras is the most obvious one, and this is what I'm going to show you today. Microphones, potentially, monitoring vocalizations for difficulties in calving and so on. We haven't done that work there, but that's a potential in the vision where we may go into. Radar sensors, they can give you indications, for example, if an animal is lame or monitor the activity of the animal. And then gas sensors, which is something that we're working on, and it's increasingly important, is how we can measure the individual animals' greenhouse gas emissions. And there is a lot of stuff, for example, in chambers, which they're trying to do that, but then that's only on a sentinel animal. They don't measure every animal individually on different diets, on different conditions, different farming practices. So I'm not having any slides on that today, because I thought I had less time. But I'm happy to talk to anybody about that, how we go about trying to give the footprint of individual animals rather than having, like a fancy Excel spreadsheet with this number of animals that breed multiplied by that many tons of methane emissions, basically. So the idea is actually, can we measure it directly for every individual? So I'll just go back into the cameras, actually. So when we were assessing this technology, we think that the cameras can do all of the stuff, actually, that all the previous sensors on the RoboCow was doing without attaching anything into the animal. So we can detect heat in the same way that we were detecting from the collar, high activity patterns. You can detect behavior, for example, eating, rumination, walking, lying, lameness, and so on. Animal welfare, lameness, body condition scoring, then feed and water intake. We can measure the feed and water intake of individual animals. We can monitoring difficulties in birth for calving. Then heat stress is becoming increasingly important in Scotland. I mean, we had work done on heat stress before down in Israel, but now we're seeing that this is kind of a big problem in Scotland as well. And if your animal goes into heat stress, potentially that could affect up to a month's worth of milk yield, basically. And then maybe another thing which we're not actually done anything work just yet, but I think from the animal science and research perspective, it's good if we can create automated ways to identify social interactions and understand more about the social behavior of animals. And what I should say, actually, that this is not only us who's working on this. There is commercial offerings today for example, to do body condition scoring. So we're not unique in that sense. They do require very expensive equipment, very expensive cameras, stereo cameras to measure precisely, the animal and the whole structure of the animal in order to calculate the body condition score and stuff on lameness. The different things have been demonstrated. What I think we're doing differently is that we are not doing it in a constrained environment and without specialized kit. Our target for this research is to go and buy a camera, IPTV camera, out of Amazon, put it up yourself, and then get the outputs from the model. So that's where we're different. So we're not saying we're unique, but we're different in that sense. And in order to do that, actually, as part of the digital design, we instrumented initially a calving shed down at the Crichton Royal Farm in Dumfries. And we installed basically 24/7 recording because we're collecting this as research data. We not envisage that operationally you will record and keep all this data. And we have 16 cameras, and each of these cameras is one of these guys' real links. You can go and buy it at Amazon, 130 pounds or thereabouts. It has 2 eyes, it has a 180-degree view, field of view, sorry, 180 degrees field of view. And we over-instrumented that, and the reason why we did that was because we were trying to assess what is the minimum number of cameras we can have to establish, first of all, full coverage, but also do the additional cameras give us additional benefits in terms of what we're trying to infer. So we're not thinking again of this operationally, we're doing that in terms of research. If you think about the data rates that we were speaking about earlier on, 450 bits per second per animal, well, it's minuscule, right? Here we're talking about terabytes of data every month for that one installation. So we need some way, again, to process that at the camera stage, at the camera level. But since we're doing that for research at the moment, I'm just going to accept that we are having to manage that data, and it's a challenge, to be honest, and it involves, even this day and age, us driving down with a big hard drive to lift all this data, because the SRUC internet cannot cope, basically. We're killing it. So with the stuff that we have today, basically, right? So we can train models. So this particular model was trained in something called YOLO. You only look once, and then it can detect the animals at different states, right? So we have at the top, we have the standing animals, the lying animals, and what you see in that star, you see the transition from standing to lying. If we cannot see the full animal in view, then that's an unidentified posture. I don't know if that animal is sitting or standing. And that is what, in real time, that's what's been processed. But then if you aggregate it, then you can see something like that. So in this visualization, at the background, there's different cows, and the heat map is just a background, right? So it's not that the cows are there. The heat map is where the cows would be between midnight and 1 o'clock at night. So you can see, this is a calving shed again, right? You can see at the bottom, most of your animals are sitting down, lying down. Well, there's a little bit of standing up, going maybe visiting a little bit on the feed phase. But if I play that video, then you can see as the different patches, the animals move through the night. But then 7 o'clock in the morning, feed is being delivered, and you can see the big heat map on the top, basically, where the animals, all of them, go to feed. And then they're going to go lie down, roam about. And then again, the next feed, about 4 o'clock, I think, in this case, there's going to be another heat map. And they may go through multiple visits through the day. So again, that's another visualization that you can use to identify, where your animal is spending most of the time. This can be used, for example, to identify areas of the shed where they have drafts, maybe in the winter, or areas that the animals prefer during the summer if it's too warm, for example. So that may allow you to actuate, for example, ventilation and so on. But if you process that over, multiple days, basically, you can start getting statistics about what your animals are doing. So you can say, for example, 16% of animals are lying down, 18% standing, and 20% are eating. And then you can trend that over a period of time. And if you have deviations from that, then you can start asking questions on why and how you manage that. And this one is nothing complicated. This model is very trivial to train. But I think the big nugget here, sorry, I have to say this one as well, sorry. I'll tell you about the big nuggets in a bit. But the other thing that you can do is you can assess, for example, contention into the feed phase and how you're stocking your shed. So here we did an analysis, we took all the animals that are sitting in front of the feed face, and what was the distance between the animals, depending on the number of animals in the shed, then we can see the distance between animals. And I've been told by the animal scientists, the estimated distance between animals is about 70 centimeters. So if they're not having 70 centimeters between them, then there's no contention as far as they're concerned. However, this doesn't account if animals are more bullish or not, whether or not they're pushing themselves into the feed face or not, and if they have equal opportunity to get food. So this, again, because we know the locations, we can estimate, if the animal is at the feed face or is standing behind it and it's queuing, then again, we can estimate also all these metrics for contention. And that mostly for understanding, how do you stock your shed, and if there's any design change that you can make to your shed. But sorry, what I was going for actually is that all that stuff that I've shown you was herd level statistics, okay? It was not individuals. And the difficulty is, can we get this information, and that's what we want, per individual, because I think this is the most important thing. And there is different approaches. There is different approaches published in the literature trying to use visual identification. However, I'm not very convinced that this is robustly done, right? So, for example, we have five animals with very unique patterns, a brown animal, a white animal, and a black animal. Surely they're discriminative enough to be able to detect them with high accuracy. But if you go to different cattle breeds, then this may not be possible. Also, the animals' patterns are changing through the day. For example, they're sitting in muck, then that will change the visual appearance, confusing different algorithms. So either people are doing that by using visual appearance, basically, or they're doing them in constrained spaces. So after leaving the milking parlor, they scan an RFID reader, and then for that length of the race, they know which animal is which, then they stop tracking. But what we're trying to do now is track the animals for a very long time, basically. And what we're coming up with is, it's not dissimilar basically to the constraint case, but we have an additional step that we need to do. We just install different RFID readers to different locations around the shed, so around the water troughs, for example, or the feed face, if they're using, for example, Hoco feeders. And then we can get an RFID and we can tell which animal is which. And then because we have this overlap of multiple cameras looking at the area within the shed, can we basically lock that animal and track it continuously? And when I say continuously, I mean long term. I don't mean 1 minute, I mean hours, right? So it's a different challenge in trying to do that. So there is cases where this long-term tracking will fail, then you can default back into visual appearance identification, but you have the prior frames as an anchoring point to do this correctly. So let me show you a little bit how this is done. I mean, let me show you the problem first, right? And why this is very difficult, right? But let's take that scenario. You have 4 animals in that shed, and then we have this cow 1, which starts moving, and then we can, measure distance travel and so on and so forth. But as soon as it goes in front of cow number 3, then we lost track of cow number 3. We, all as humans, we realized that there is 2 cows there, right? It was cow number 1 that went from the front, and cow number 3 sitting behind it, and it's pretty easy for us to do, not so easy for a machine. If you ask yourself, how am I able to tell that and the machine cannot, is because you have a perception of depth. You understand that things are at different depth. So that's what we kind of realized, and can we obtain depth information, basically? And we doing that actually through something which is called depth anything. So this is a model of the cell which is trained on multiple LiDAR data sources of different scenes. So you have the LiDAR and the corresponding RGB image of the scene, and then to understand essentially the textures and can discriminate between different depths. So applying this model into that image, we get the depth information which sits on the right. And now suddenly we don't have a 3-channel image anymore. We don't have RGB, we have RGB plus depth. So now that makes our life a little bit easier. And I'm not going to take you through the details, basically, but in short, basically, we have the raw footage, we create different tracklets, we use different segmentation to define which animal we want, we get the depth, we create point clouds, and then the bit which is complicated, basically, is how do we get the two camera views, because we have multiple cameras. So this cow is occluded from the one camera perspective, but not from the other. So can we calibrate the two cameras, actually, to hand over the tracking from one camera to the next? And if we combine the two camera locations together, you can see them, then we have two different orientations for the same animal. So we can track now the animals in 3D space, essentially. So when we occlude cow number 3, then we have it unoccluded from the other camera view. And if I show you, sorry, this is actually their motion, so you can track all their motion in 3D space. And from that motion, we don't lose the tracking. Sorry, that's different steps on that. So if we take this together and we merge them together, then what allows us to do is just to recreate that scene in 3D space. And what you're seeing here, actually, it's a 3D rendering of that from the one camera view, and now you're going to see a flyover, so we can see what the other camera sees. So in this case, the cow will start moving towards us because we're on the opposing camera view, but we don't have the problem with occlusion of occluding cow number 3 from the previous scene. So we've extended this work, we extended this work into working with multiple cameras. So at the moment we have full coverage. There is obviously, as you can imagine, different issues. Different cameras have different beliefs, and we need to come in some sort of an agreement between the cameras. And the idea is actually trying to do that with assigning different weights to camera decisions. The other bit, which is kind of complex, is how do we calibrate? And with this one, we don't calibrate, is the simple answer. There is other work published in the literature, which requires a lot of heavy-duty calibration. But again, like I said at the beginning, one of the requirements was, you can go and buy a camera off the shelf of Amazon, put it up into your shed, and on you go, without any interruption. No calibration, no nothing. So that's what this allows us to do. So I think, in summary, so I just covered the computer vision work. In summary, I think we have a lot of device fragmentation. I think this AI thing gives us the opportunity to work towards removing that, sorry, what happened there? Removing these multiple devices that we're deploying to our animals. And this remote ambient sensing, I think, is the way things are going to go forward in the future. That's going to lower the cost and faster adoption. Like I said, there is existing computer vision technology which has been used. It's typically quite expensive, requires calibration and so on and so forth. So this additional insight and the stuff that I didn't cover, if you can do all the stuff together, heat stress, animal health, lameness, body condition score, social interactions, all that stuff actually, together I think provides you more insight, which I think ultimately will be able to feed into changing our management practices into the farm, but also informing policy. I think if we combine that along with the greenhouse gas emission work that we've been doing, we're not quite there yet to attribute individual animals. We're working on that, but I think combining the measurements on the shed with the location of the animals together from the camera system will allow us to create individual footprints for every animal. And that's my end of the talk, but I'll be happy to answer any questions. Thank you. Thank you.
Thank you, Christos. Check, have we got mics in the hall so everybody can, those online, the recordings can hear? Yeah. Great. Any questions for Christos? Well, thinking I'll start off. Yeah, no, thank you for that. I mean, I think it's really interesting, that we can see how some of these developments on farm could ultimately feed through into kind of more data that would be relevant to the work that we do in supporting policy. But, and you say the cost is coming down, which obviously is one half of the equation. Mm-hmm. How quickly do you think that the benefits are going to be strong enough for us to see uptake of some of these technologies actually on British
I
farms?
think this was intentionally the design of the work that we've done. We want, like I think I said multiple times, we want to do low-cost devices. We don't want basically to have to install a very expensive system, so the farmer can go get a camera, get the open source model that we're providing, and then directly. I know he assumes certain IT literacy, but I think there's going to be agri-tech solution providers they're going to jump up and take that model and deliver it to the farmers as a service rather. We're trying to lower that adoption cost basically, and my hope is that this is going to get adopted, especially from the small farmers, because there is another thing. We have the big farmers, maybe they have a lot more money to invest in technology and monitoring than animals. The small farmers not so much, and they will be thinking a lot more, which technology they're gonna use. So clearly, I'm not saying to the big farmers, drop your collars out and start getting video technology. We're not at that stage yet, but we hope that this is a path towards that.
Thank you. Okay, questions? Oh, Jenny.
Hello. Yeah, that's working. I'm Jenny Purcell from Scottish Government. Just following on really from Ian's question, I wondered if you'd done work with other domestic species, and I'm thinking particularly like pigs and chickens, which are kept very intensively, but maybe relatively low amounts of human staff per numbers of animals.
Yeah, so I haven't done yet work with other species. I have a PhD studentship with Queen's University Belfast that was trying to do a similar thing, trying to detect pigs and track them for tail biting. So this is one approach which is going to use the same basically technology of tracking the animals, seeing which pig is biting which tails, which other pig, so you can isolate it. This is kind of the use case. And the other bit, that's why I had also the audio. The other bit which kind of looking for and trying to build a project around is around monitoring coughing in pigs, for example, for respiration issues. So again, these cameras, the reason why we're deploying that, there is technologies like out there. For example, SoundTalk will monitor coughing in pigs, is one that has been out from Belgium. However, it requires a very expensive microphone array. So I'm all about trying to lower the barrier and say, okay, you can use these cameras have microphones. Can I use these cameras to localize which pig is coughing?
Thank you.
Any more questions? Sorry, you're going to get very fit.
Hello, I'm Anna from EPIC and Roslin Institute. So you put all the cameras on walls. Have you considered putting them on ceilings? Because then you have, better maps of tracking the movements and stuff.
Yes, so thanks very much for that question. We have put them in ceilings as well. The reason why we just insisting on putting them sideways is so we can maintain the visual perspective for the face to be able to detect the rumination. The top-down, the nadir cameras will be very helpful and it's going to make our life easier in terms of tracking, in terms of location, but we're going to lose the ability to see the jaw, basically. And that was a conscious decision. In fact, we have another deployment, which I didn't show you today, in the Barony Hall with SRUC, and that has both, because we're trying to compare the two, basically. But it requires additional cameras, right? We're trying to lower the cost as much as possible.
Okay, thank you. Thank you.
George.
Hi, George Russell, Mordan. I was wondering whether or not there's an upper limit in the number of animals you can track with your current version of the software, and also whether or not it can also be applied in outdoor environments.
So thanks very much for that question. So I don't know what the upper limit is. At the moment, this shed that we're having in Crichton is a calving shed. There's a high turnover. Animals are, coming in calve and then they go out. So the number of animals is changing all the time. The other installation, the Barony, I think it has a fixed herd size, and we need to do the analysis to see, what is our limit and how much we're losing. We need a lot more validation, right? I'm certain for that, right? Now, for the outdoors, we did consider the outdoors. The issue is coverage, actually, outdoors. So if you have multiple fields and very long distances, how do you track that? And that's one of the reasons why I'm not saying to the farmer, check out all your color systems and go with cameras, right? Because some of the animals get placed outside rather than indoors. We could potentially do things like, for example, have a mobile posts and have the cameras to track some of the activities, but you're not going to be able to tell rumination or eating. Well, you can probably tell eating because you can see the head down. The rumination is going to be very hard to detect. But we're looking from it from the perspective of social interactions and synchrony between the animals, trying to quantify sort of positive welfare. So we're looking outdoor deployments for that reason.
Hi, Maria Costa from SRAC and EPIC. I have more of a practical question that I'm not sure if you'll be able to answer, but I'll ask anyway. We've been seeing a huge development in terms of biosecurity in different species, pigs much more than cows. But how are these sensors adapted to biosecurity and the cleaning that has to be done after each production round, specifically in pigs, but in cows, again, we'll start seeing those more often, cleaning and disinfection?
Okay, so I haven't thought of that. Thanks for bringing it up. If I understand you correctly, you mean, how do we clean, for example, the parlo? Is that what, yeah?
Yeah.
So I don't see why this cannot be adopted to clean the parlo, although you're not monitoring the animal anymore, you're monitoring the surfaces. And if there is visible signs, then I'm sure, it's going to be very hard to adopt the technology, basically.
Yeah, because in the case of pigs, you might have, I don't know, if you have thousands of pigs in a farm and you have sensors in every pen or in every room, then I don't think it's very feasible to remove them to clean the whole thing with the power wash and all the disinfection and drying and all those things, because it might damage the sensors, I imagine.
So the sensor is just a camera, and normally it's mounted quite high. Do you think it needs disinfection at that height?
Ideally, yes, but it's not very done on a routine
so
basis.
I haven't considered what you're highlighting, right? And maybe we should have a chat.
Maybe. Thanks.
Definitely we'll have a chat.
Any more questions? I think I'm aware of some of our colleagues at APHA have started looking at some of the scope of milk production data, the kind of a syndromic indicator. Now, not really efficient, but if anyone was willing to just kind of chuck that into the conversation, that would be quite interesting. But the point being that I think we can all see how the production information is relevant in that respect. And we know that BTB3, one of the signals, was milk production drop in the Netherlands. Maria?
Is it working? Yeah, it is working, sorry. Yes, so the sensors are really good. You can see you can get lots of data. But we know that we struggle getting people to work on the different farms, and maybe they speak different languages, and sometimes the levels of literacy are not as high as expected. How do we intend to bridge the gap between getting all of this information and getting it onto the ground to the farm staff?
Yeah, I mean, that's a good point, actually, right? And we've seen that before as well. With the collar system is not new by no means. And myself speaking to farmers, they kind of stop using certain bits of kit because it's on 10 different systems. And now what I'm going and saying, okay, now you need to use one more, right? So yeah, I think that's an important issue that needs to be considered, for wider deployment. I guess what I'm kind of contemplating is if this has been successful, basically, and can remove all these additional sensors, and you have one system that you need to integrate with your farm management software, maybe it's more appropriate for them to utilize easier. But I had this conversation many times before about integration of different data streams and present this to the farmer. It's an issue that I don't think anybody has an answer to, right? And it's not a technical, I should say, it's not a technical barrier in bringing all these data sources together.
It's a social barrier.
Or companies not actually kind of willing to allow them to use the data. They want to lock you into a specific ecosystem, for example, right? So it's a commercial decision rather than a technical decision, I think.
Thank you.
I think maybe, sorry, may I add something on that? Maybe I think that's the role of government, maybe to kind of force sort of tech suppliers to provide this data. So maybe regulation should come along to that to kind of force the companies to do that. I don't know, that's just a thought.
Great. Thank you.
Thank you.